All right. Okay, it's going. So these are the electronegativity values. I will give you any of these I want you to use on a test. Really the only calculation in this set of stuff we're doing here is right here, and it's a simple one. But notice all the atoms have electronegativity values, and the higher the electronegativity value, the stronger a tendency it has to pull the electrons towards itself when it's in a molecule. Covalent bond, not necessarily covalent bond, I'll show you in a second. Okay, so this top right corner, these are the strongest electronegativities. So fluorine's the strongest. And here's carbon, 2.5 compared to 4.0. So the 4.0 tells you that it pulls the electrons towards itself more than the carbon. So this side is slightly negative and this side is slightly positive. And all of these are the same way. Every one of these bonds has some polarity to it, what we say polarity. You could also call it a sort of object. Physicists, and I guess chemists too, we call it a dipole. It's two poles, a negative side and a positive side, so we call it a dipole. And we use this little Greek delta, D positive, D negative, to show which side is positive and which is negative. So that's a polar bond, a polar covalent bond. We also do, we might do this. And this arrow is indicating that's the positive side and that's the negative side. And that's literally the symbol used to indicate a dipole. So polarity, dipole, polarity, dipole are kind of synonyms. All right, so there's that. All right. So you look at those electronegativity values to decide which one wins the tug of war, and the one that wins the tug of war is slightly negative and the other side is slightly positive. Comparative values, so there will be an example right here. You calculate what's known as an electronegativity difference. That's kind of what I was explaining. This is showing, so if both atoms are the same atom, if it's F2, two fluorines, obviously they pull on it the same amount, so there's no polarity. They're both pulling on the electrons the exact same amount. So one of them isn't winning the tug of war, so those electrons are even. But if one of them is a different atom and it's got enough of an electronegativity difference than the other one, it wins the tug of war and you get some polarity. So that's kind of what I was doing with the shading. Let me get to this. That's what I was trying to think of. Polarity, dipole, and dipole moment, they're all kind of synonyms. So don't get confused if I'm using them interchangeably. Okay, so you do this. You want to decide if something's polar or not. Where is the... what's in your lab? Well, I'll just write it down, but it should be in here. Dipole. Yeah, comparing covalent. Come on. Well, I must have gone past it, but I'll write it down. It's got to be here. All right, let me go back to this example. We'll have that. All right, a slightly more analytical way to look at these. So these aren't full molecules. This is just saying boron chlorine bond, carbon to chlorine bond, phosphorus to fluorine bond. So let me sketch this out. So to be a little more analytical about these dipoles, or this polarity that might be in a bond, got B, Cl, and CCl, so carbon to chlorine, and P to fluorine. All right, and I need to, all right, if you want to compare the polarity among these, like which one has the strongest, the biggest imbalance, that is the biggest negative charge, biggest positive charge, you would use this chart, and any of these values I'll give you on the test, but there is this trend. In general, going left to right, electronegativity increases. And going from bottom to top, electronegativity increases. General trend. All right, boron 2.0. So boron 2.0. What does it say for chlorine? You see it?
It's a 3 even. I can see.
Yeah, 3.0. All right, I'm going to do absolute value, and that's a minus sign, so that equals 1.0. All right, here's the scale. I couldn't find it in there, but from 0 to 0.5, if this resulted in 0.5 or less, the 0.5 does indicate that there's a little bit of polarity, but for all intents and purposes, it doesn't show up in any property, so we just say nonpolar, even though, so this 0 to 0.5 is what I'm saying is from this equal sign. And then 0.5 to 1.9, we call that polar, which is what we're talking about. That would be a polar bond. If this result is between 0.5 and 1.9, we would say that's a polar bond. There's a negative side to it and a positive side to it. And then greater than 1.9, we'll say if the electronegativities are that much disparate from each other, then one of them has stolen the electron from the other one, and it's an ionic bond. You literally have a positive ion and a negative ion. Or maybe it's taken 2 electrons from it. So if you have an electronegativity difference of greater than 1.9, it's an ionic bond. So we're kind of focusing here. So this one, so what this is saying is, since chlorine is larger, this side's slightly negative and this side's slightly positive. Chlorine is 3.0. Can you see carbon?
2.5.
2.5. So what do we get here? 0.5. And you always want to do absolute value. That way it doesn't matter which one you put first. So that, of course, equals, you might say that's barely polar, but it's right on the edge. P to F. F is 4.0. Phosphorus is 2.1. So what is that? Is that 1.9? So that's, I'd say, very polar.
So would you consider the 0.5 to be polar? Just barely?
Yeah, some books do, as a rule, they say 0.5 inclusive here, and some of them say it's inclusive here, and then it's 0.5 or no, greater than 0.5 and 0.9. I won't tend to put you right on a cusp like that. I'll get in between, so you're certainly in here, or certainly above here, or certainly below here. But that's the type of question you could get. Is this bond polar, nonpolar, or ionic? And you would do this electronegativity difference, get your result, and then use this scale to decide. So if you had these in a molecule, that's 1, that's 0.5. Just to give some indication here, I'm going to put a little tiny negative, a little tiny positive, and then a really big negative and a really big positive, just to show that this is really polar, this is polar, and this is like maybe barely polar, but almost non-polar. So you can use those electronegativity differences. And what this is indicating is, like, if I had, I'll just put hydrogens here, that's saying that there's polarity here and there's polarity here. Since hydrocarbons are so common, I think this is 0.4 or 0.5. So this one's polar. I'll use this. I'll go, here's a dipole, there's a dipole. But there's no dipoles here, because if we did the electronegativity difference for carbon and hydrogen, you'd be down here in this range. They're very close. What we got? 2.5 and 2.1. So you get 0.4, so it's definitely nonpolar. You see what I'm doing? Polar, nonpolar. So, but the general trend, you can get questions like this. Which one is more electronegative, gallium or chlorine? And you can do that by going, there's gallium and there's chlorine. Chlorine is up here in these really electronegative ones. Gallium's down here. So chlorine is more electronegative than gallium. There is this weird little hump right here, but if I ask you in general, just out of the blue without that chart, which one's more electronegative, just assume left to right gets more electronegative and bottom to top gets more electronegative, the way this is indicating. But you can see it's not a perfect trend. You've got this hump right here. So bond polarity, electronegativity. All right, good. So I introduced you to Lewis structures. But really, that sort of game of Tinker Toys is kind of limited. Because stranger things happen. So there's this set of rules that if you follow them, you can build a molecule if you're given the formula. If you're given, you can read these. I'm going to go through and do some of these to show you. But first you need to count up all the valence electrons from all the atoms that are there. The next step is what I call building a backbone. You can read these, it's probably good to know them, but let me, I could read these to you, but it'll go in one ear and out the other. It would be too. Let me do some examples. If someone threw PCl3 at you and said, make the Lewis structure. This is one that you could probably do with a game of Tinker Toys. P and Cl3, Cl is this. So phosphorus makes how many bonds? You can see from here. It makes 3. And chlorine makes how many?
1.
So just in your head, you could probably, if you wrote these down, go, yeah, I see how this connects up. Right? You got 3 chlorines. Phosphorus makes 3 bonds. But there is a formal way of doing this. And some of these, you remember the polyatomic ions? Those were molecules. They just happen to be charged. And there are stranger situations. NO is weird. NO2 is weird. So, but I'll show you what I mean by weird. But yeah, for this, I just connected that and that and that. There's a Lewis structure for PCl3. But I'm going to go through the rules with PCl3 just to get it started with it. It's worth doing easier ones first. PCl3, first we need to add up all the valence electrons. P, there's one of these here, Cl. There's 3 of these here. How many valence electrons in phosphorus?
3.
No.
Wait.
5. You get that off the Pirac table and you go 1, 2, 3, 4, 5, and then you have what I got right here. All right, and how many valence electrons for chlorine? 7, so we got 5. 3 times 7 is 21. We have 26 electrons. Valence electrons, those are the 26 electrons we have to work with. Oh, the other thing is, pretty much all of these, except for hydrocarbons, I mean, things that might look like this. Hydrogen, let's do a double bond. That's a hydrocarbon, and it kind of forms this chain. But other than that, all the examples you tend to get in a 1211 class has a central atom, and everything else radiates out from there. And the central atom is pretty much always the first atom mentioned. So PCl3. And if it's vague, which one's the central atom, I'll give you what I call the backbone. But here's how you start. PCl3, and let's say you were wise enough to know that's going to be the central atom, and then it's going to have Cl's around it, the 3 Cl's around it. So you've got a central atom, and then the Cl's go around it. The first thing you do is go ahead and connect them up with at least one line to them. All right, so I've made what I call the backbone. And like I said, if it's vague, what's connected to what, I'll just give you the backbone and you work from there. I don't think the book gives them to you, but I think the problems I wrote down are the ones that's always a central atom, and it's kind of obvious everything else is connected to it. But you would start there. We've used 6 electrons already, just by making the backbone. 2, 4, 6. We've used 6 of these already, so I'm going to go, do it over here, minus 6. So now I'm down to 20 electrons. So I'm actually working on that set of rules that I just skipped over. But you list the valence electrons, then you make your backbone with single bonds. And I use 6 electrons to do it. So now I'm down to 20. The next thing you do is start filling in the octets of the outer atoms. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Did we count those wrong? 3 times 7 is 21, plus 5 is 26. Oh, okay. Okay. This one isn't as straightforward as I made it seem. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, yeah, that's right. We're at that point where I start to lose my mind. I made it further today than usual. 2, 4, 6, that was this 6. We subtracted that. And now I had 20 electrons left. I started filling them on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I've used 18, and I have 2 left. Maybe sugar will help. All right, so this is a formal way to do this. I have 2 electrons left. If you have electrons left, you stick them on the central atom. Oh, and then as pairs. Maybe that's obvious now. Now I do this. Now I'm down to the end of the electrons. Now you look at your structure and you go, does everything have an octet? And when it's a bond, this one gets to share those 2 and count it, and then this one gets to count those for it as well. So this one has 8 around it, 8 around it, 8 around it, 8 around it. Everything's good. That's the Lewis structure. And that is what I had before. And yeah, it really was just the atomic Lewis structures connected up just connecting the dots. But like I said, it's good to start with easier ones. They go progressively. All right, HCN. So it says draw the Lewis structure for HCN. The only exception to the first atom always being the central atom, if you see hydrogen first, it's not the central atom. It really can't be. So if it might have hydrogen in the front, but just ignore that. The next atom is going to be the central atom. So I know that sounds a little vague, but the backbone here, I would just do that. But how many valence electrons? So nitrogen has how many valence electrons?
5.
Got 5. Carbon has
4.
And nitrogen has?
Hydrogen.
Hydrogen has 1. So that's 10 total. We've used up 4 here just to make our backbone. 2, 4, so minus 4, we have 6 left. Now I start filling the octets on the outside ones, but hydrogen is one of those exceptions. It was hydrogen and boron. It's not going to get any more. Hydrogen is just going to stop there. So now I'll go 6. So now I'll fill the octet on the outer atoms, but I ignored hydrogen because it doesn't get more. So minus 6. Now I'm out of electrons. And now I'll go, does everybody have an octet? But they don't. So what you do is, if everybody doesn't have an octet, you start grabbing whole pairs from one of the outer atoms and making a bond there. There. Now, so I moved that pair into a bonding pair. Now do they all have an octet? Nitrogen had an octet here. The problem was carbon. It only had 4 electrons around. It still needs 4 more electrons around it. So in order to fix that, I took this bonding pair to make a bond. Nitrogen still has its octet because it still gets to count those 2 and those 2 as part of its. Carbon counts these 2, these 2, and these 2. It only has 6 now. So now I can fix that by putting that there. I think this is the 3rd or 4th rule in that list. If you don't have full octets, then you start borrowing pairs from the outside to make a bond to the inside until that inside atom has its octet. Now they all have an octet, at least all of them that are going to have an octet. That's it. That's HCN. I think that was the 4th rule in the list that we just went through. But again, this is such a simple molecule and there's nothing weird about it. Don't be afraid to look at it and go, nitrogen makes 3 bonds, hydrogen makes 1 bond, and carbon makes 4. You can kind of piece it together if you want to sit and think about it. Get a bond there, get a bond there. Now you got these 2 you can make a bond, and you got these 2 to make a bond. You end up in the same spot. It's not always that straightforward to play the Tinker Toys game, which is why we're going through the formal rules. Okay, good. All right, so there's that twist. Borrowing pairs of electrons from the outside to make a bond to the central atom. Yeah, let's do carbon monoxide, CO. CO. There's not really a central atom here, so I'll start like that. Oxygen has 6 valence electrons, carbon has 4, so I'll start with 10. I've used a pair already, so minus 2. I guess in this case, you just try to put them all the way around. 2, 4, 6, 8. This is one you have to tinker with a little bit because you might do this instead, filling them out. But let's say I call these both the outside atoms. Yeah, these sets of rules are never that complete, but if I'm sitting here going, I've got to have an octet around all of them, and I've only got 8 more electrons after that first one, and now I have to go in as pairs, I might have done that, or I might have done that, but either way, the only way to get the octet around them is to start taking one of these pairs and make a multiple bond. Take another pair here, make a multiple bond. I believe that's it. CO. Didn't think they did formal charge yet. So that might be premature. Well, they shouldn't have given that as an example yet because we haven't gotten the formal charge. All right. Let's do BrO3 negative. So there's one of our, what do you call it? Polyatomic ions. All right. Br will be the central atom. 6 valence electrons for oxygen, 7 for bromine. So 3 times 6 is 18. Plus 7. Let me do this. Polarity out of the way. Br, there's 1 of them. Oxygen, there's 3 of them. Times 7 times 6. We get 18 here. We got 7 here. That gives us 25. All right, I'm going to add 1 more electron to get to 26. Do you know why?
The charge.
Because it's got this charge. It's telling you it's got an extra electron over and above the valence electrons. If this was positive, I would subtract an electron from here. So when the molecule is charged, when it's a polyatomic ion, you add or subtract electrons accordingly. So what this is saying is we actually have 26 electrons. Now we'll do this, Br, and we'll make our backbone like this. 2, 4, 6, minus 6, I have 20 left. 2, 4, 6, 8, 10, 12, 14, 16, 18. 4, 6, 8, 10, 12, 16, 18. Minus 18, we have 2 left. I'm going to put those in the center. Minus 2, we're down to 0. Now we check to see if we have an octet, and we do have an octet everywhere. So that's the complete Lewis structure for BrO3 negative. I wanted to do that one just to, notice I said plus 1, but this is minus. But minus means there's an extra electron, and that's what we're counting up here. So you've got to add an extra electron when it's 1 negative. If it was 2 negative, you would add 2 electrons. If it was plus 1, we would subtract 1 electron. If it was plus 2, we would subtract 2 electrons from the valence electrons. Oh, this bit of notation here. For Lewis structures, if it's charged, kind of the formal way to write it is to put that bracket around it and put the charge there. That's the correct way to do it. If it's not charged, you don't need brackets. ClO2. I think we need formal charge. Well, let's see what happens. ClO2. And it's 1 negative, right? Okay. 7 for chlorine, 12 for the 2 oxygens, and then 1 extra electron. So 20. 7, 8, 9, yep, 20. 20 electrons to work with. Make our backbone. 2, 4, so we've used 4, so we're down to 16. 4, 6, 8, 10, 12. 14, and I'll put these down here. 16, 2, 4, 6, 8, 10, 12, 14, 16. That does, yeah, we didn't need formal charge there. We use formal charge when things get a bit weird. So there's the Lewis structure for ClO2 negative. Oh, no, not yet. Yeah, let's do PO4 3 negative. PO4 3 negative. Oh, we moved on to molecules. 5 for phosphorus, 24, 6 times 4 for oxygen, and I'll say plus 3 more for the 3 negative, so 8, that's 32, 9, 10, 11, 12, that's 32. 2 electrons to work with. P will be the central atom, and we'll just make a backbone like this. 2, 4, 6, I've used 6 electrons. So what is that? 6. 2, yep. All right, and now 2, 4, 6, 8, 10, 12, 15, 16, 18. What does that leave me with? Too tired for this. Is that right? Yeah, that's right. My brain can't do that subtraction. Is that right? 26 minus 18.
Oxygen?
26 minus 18, is that 8? Thank you. 8, 9, 10, yeah, it's 26, okay. So I've got these octets. I've still got 8 electrons left. Seems like way too many. Is this right? Oh, that's what you were saying.
Yeah.
Fuck. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So minus 24, we're down to 2. And since we have 2 left over, we're going to put them on here. Minus 2, and 0. And this is the first odd exception of there being more than 8 around an atom. And it's legit, it's correct.
Well, isn't there technically 8 because or the first you only subtracted 6, shouldn't it be minus 8 because of the 4?
Yes.
Of the 4 bonds?
Okay, yeah, we haven't gotten to that exception yet. Yeah, that screwed it all up. 2, 4, 6, 8, so this should have been minus 8. which made this 24, which got us down to 0. Okay. I guess I'll stop before we do that. But starting with phosphorus and any of the atoms down below, any larger, you can actually have more than 8. So an exception to the octet on the high side instead of the low side. That's where we'll pick it up next time. We do have lab, and then you'll go enjoy your 4th of July, and I'll see you next Tuesday, but come to lab. I'm not saying bye for the week. I'll see you in a little bit. Somebody staying after lab? Make up the...
Yeah.
You do? Yep.
Tuesday's lab.
Oh, Tuesday's lab.
And
No.
Thursday.
I thought somebody had to make a new test. I have to go add up y'all's tests between now and lab. So. Oh, did I say that? That I'll give you your tests after lab?